And now we get to explore the next major topic in physics, and this is the concept of energy. And so energy obviously is a very, very common word, and we all have our own understanding of what energy is, but in a bit more of a scientific, physicsy kind of way, energy is regarded as related to the idea of either heat or work. Essentially, it's like quantifying or measuring the potential or the work that an object is doing or having done onto it. It can also be related to energy related to something to do with heat as well. And so it seems a little bit abstract at this point, and probably the best way to actually understand the concept of energy is through talking about the different types of energies that we know about and how they relate to each other and kind of how you go from one type to another type. And that's going to be an important part of our look at energy. The other big part is going to be the idea of conservation of energy. Just as we've already talked about conservation quantities when it came to momentum, conservation of energy is going to be also very, very critical in the usefulness of the concept. Okay, so we are talking about energy, but I think it's best if we begin with an example of energy. And one of my favorite examples to show a whole bunch of different types of energy is through the Olympic sport of pole vaulting. Seems kind of obscure, but it's actually fantastic when it comes to energy. Let's take a look. Okay, so we have our pole vaulter here, Armand Duplantis, who holds the world record for the highest pole vault. And you'll see what pole vaulting is exactly in this video. But what I want you to look at as we watch this video is the different types of energy that you see. And we're not going to use the scientific names for those energies just yet, but let's try to identify them. Okay, there he goes. This is all in super, super slow motion. He's actually running really, really fast. So running, he's got running energy. And we know that motion is related to energy. Okay, so now notice what he does with the pole. He's running at such very, very high speeds. And the pole comes down and goes into the pole area. And then notice that bend. Look at that bend in the pole. And then finally it straightens up. Look how high he is in the air, how he's defying gravity and finally coming back down. And as he falls, he gets faster and faster and faster. So really quickly, running energy into kind of like bendy pole energy, into height energy, and finally into speed energy as he comes back down. And so we'll just watch that again carefully. And if we were to use the right lingo here, the actual types of energy, it's kinetic energy of motion, it's spring energy in the pole, it's gravitational potential energy when he gets up high, and finally it's kinetic energy again as he falls to the ground. Okay, I'm going to show another jump now, and this is from the same jumper, nicknamed Mondo. And Mondo is going to get the world record here. He's going to jump 6.18 meters. That's crazy. Going over something that is triple my height, more than triple my height, is incredible. And there's no like mechanical energy or any kind of energy source that's coming from anywhere outside of himself. All of the jumping energy he has is all due to his own motion, to his own running, to his own technique, and all of that kind of stuff. The pole, what about the pole? What does that do in this problem? Well, let's compare the high jumper to the pole vaulter. So in the high jump, I won't show that, but basically people are running and then they jump and they kind of do that flop backwards, and they jump about 2.4 meters. That's a very, very high jump. And so how can pole vaulters go 2.5 times higher by simply using a pole? Well, what they're able to do is they're able to transfer their running energy, this kinetic energy that I mentioned, into gravitational potential energy or height energy much more efficiently than our legs can. And so even if we're running really, really fast, that's a lot of energy. But then when we take off and we jump, our legs are actually not good at transferring that running energy into a leap, at least a vertical leap. But probably this way, maybe they're a little bit better. But regardless, this is a vertical problem. And so what the pole specifically does is it takes that kinetic running energy and it converts it first into a flexible, springy type of energy in the pole, and then that pole energy is converted into the height gravitational energy. And so by basically having this in-between step, we have a more efficient means of transferring kinetic energy into gravitational potential energy. Let's watch this world record-setting jump. And so here he comes with his kinetic energy. Pole goes down. Look at the bend, look at the bend. And so all that kinetic energy is turning into a flexible energy, which then he uses his technique to straighten it out and get as much height as he can get. Look at that. That's amazing. Wow, 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 wow. Am I in the way of this picture? Kind of feel like I'm in the way of this picture. Okay, one more time. We're going to watch that one more time. This time without me blocking it. Okay, so here he comes. How's it going? Kinetic into spring potential energy. That's a type of potential energy. It's storing energy in there, and then it releases that energy, and it converts it into gravitational potential energy. He ends up going very, very high, and now he has a gravitational potential energy 6.18 meters up, and as he falls to the ground, that gravitational potential energy is turning back into kinetic energy. And he's able to do that very, very efficiently. Fantastic, fantastic. Okay, so let's get that example down. We'll write it down here. I want us to take, for example, a pole vaulter. Who transforms running energy into jumping energy. Again, these aren't the official words. I just want to first write it down in kind of like everyday lingo, and then we'll get a bit more in with the jargon of physics. So take, for example, a pole vaulter who transforms running energy into jumping energy. And what is actually happening in this problem is kinetic energy. That's what we call the energy associated with motion. Becomes, or is transformed into, elastic or spring potential energy. Now, it's not really a traditional spring, and so perhaps the word elastic is more appropriate here, but they're essentially the same thing. And finally, once the bent pole is straightened, that potential energy in the form of elastic potential energy is again transformed, this time into gravitational potential energy. All right, so what I'd like you to do now is to think about where his kinetic energy came from. if it seems like one type of energy keeps transforming into another type of energy, let's take it even further back. Where did our pole vaulter get the kinetic energy that he needed to run in the first place? Think about that. Comment on that. Some people might be thinking about the chemical processes in his body, in his muscles. Well, where did those get their energy from? Some people start to think about the idea of food energy. Well, where did the food get its energy from? Follow it backwards, see how the different types of energies came about. Well, eventually, whether he was eating meat or eating vegetables, the energy for the food comes from photosynthesis, which is energy from the sun. Where does the sun get its energy from? Through nuclear processes in the core of the sun. And so following this energy trail backwards is starting to indicate to us the idea that energy is transformed from one type to another and not necessarily created, as we will see much later. But let's introduce two types of energies now that we're going to use throughout this topic. And those ones are going to be the kinetic and gravitational potential energy. So let's call it gravitational potential energy. And let's define what we mean by potential energy and how that's different than not potential energy. We don't put the word potential in front of kinetic. Well, when we use the word potential, usually what we're talking about is kind of like energy stored in a process by some method. And that object has the ability to release that energy in a fashion. And so when I take an object and I give it some gravitational height, what I'm talking about is the ability for it to release that energy. Let me give you an example. Okay, so let's look at an object like this hockey puck here. And if I was to say move the object from this location to this location, well, we say that what I'm doing is adding gravitational potential energy to the object. What that means is that by shifting the location of this puck, this now has the potential to convert that energy into a different form. So if I was, let's say, to drop it here, it's very quickly going to turn into kinetic energy. Kinetic energy is the energy associated with motion. The faster something moves, the more energy it has. So gravitational potential energy seems to imply that the higher something is away from the surface of the Earth, the more gravitational potential energy it has. That's true to an extent, but what we're actually going to find out with gravitational potential energy is it depends. Gravitational potential energy is not an absolute value the way kinetic energy tends to be. Gravitational potential energy is dependent on where you're measuring from. It's a relative quantity. It tells you the gravitational potential energy compared to a location. So let's see what we can learn about those two through using something we understand very well, and that's kinematics. So let's introduce gravitational potential energy and kinetic energy through kinematics of free fall. And so we've done the kinematics of free fall. It was easy enough, I would say. And let's take an example of a situation where we have a mass, and that mass is in free fall, and so it's accelerating downwards. If I, as usual, make my axes in the y direction positive upwards, then what I'm going to end up with is an acceleration of negative g. Okay, so that's my situation. And of course, I have kinematic equations that describe the motion of that mass as it falls. One such equation would be equation number 3, our famous Vfy squared is equal to V initial y squared plus 2 times acceleration in the y direction multiplied by y final minus y initial. Okay, so what I want to do is I'm actually going to rearrange this equation. And instead of having the Vfy squared and solving in terms of that, what I think I'm going to do is I'm going to put all the initial stuff on one side of the equation and the final stuff on another side of the equation. So first thing, let's multiply out our brackets. So Vfy squared is equal to V initial y squared plus 2 multiplied by the acceleration times y minus 2 times the acceleration times y initial. And so basically these terms here are just coming from taking the top bracket and expanding it out. And so now multiplying them out, we end up with V initial y squared minus 2ay y initial. And the other side of the equation, we're going to have Vfy squared. And that side goes to the other. We get minus 2ay y final. But we know what ay is in this case. It's just negative g. Let's put that in right now, giving us V initial y squared plus 2g y initial is all equal to Vfy squared plus 2g y final. All right, so it's basically saying the initial velocity squared plus 2 times gravity times the initial position is equal to the same thing at the final position. All right, so what does that mean? Nothing. Until we do a little bit of multiplication. Let's multiply both sides of the equation by 1/2 m. Why? No good reason right now, but you'll see what we end up with. So multiply both sides by 1/2 m. And so that means you multiply every term by that amount. And what we end up with is 1/2 m V initial y squared plus, okay, so if I do 1/2 m on that, the 2's cancel, and I've got an m, oh no, I'm multiplying by m, sorry. So that should be up here, and so we're left with mgy. Okay, good. Just making sure. So this is mass times gravity times y initial, where the 2 has been taken out by the half. On the right-hand side, we get 1/2 mvfy squared and mgy final. Okay, so for a few of you, this looks very, very familiar. 1/2 mv squared, what is that? Mgy, what is that? For those that have seen the equations before, that is the kinetic energy and the gravitational potential energy. Allow me to copy and paste this onto my next page to describe what each of these terms is saying. This term here, 1/2 mv squared, is our kinetic energy. It's the initial kinetic energy. This term here, that is the gravitational potential energy. More accurately, the initial gravitational potential energy. Let's write it fully out since it's new to us. And all of that is equal to the same thing, but the final version of them. And so this term here is our final kinetic energy. This term here is our final gravitational potential energy. And so we've done a few things here. Not only have we taken our kinematic equation, an equation that we derived, that we know is well established, and found terms for energy, different types of energy, but what we have is a conservation equation. This is basically saying that the total energy of our object as it falls is constant. So the gravitational energy here plus its kinetic energy is equal to its same thing at each of these points as it falls. Now, you and I know that it's transferring one type to another. It has a higher gravitational potential energy at the top, but as it goes down, the gravitational potential energy goes lower and lower, but the kinetic energy gets higher and higher and higher. Eventually, by the end, perhaps, it's completely kinetic energy. We could also write this equation in the following way. K initial stands for kinetic energy plus UG initial, where U is always the symbol for potential energy and UG means gravitational potential energy, and UGI is, of course, initial gravitational potential energy. All that is equal to the final kinetic energy plus our final gravitational potential energy. So what we have shown is the conservation of energy for free fall. Now, this is assuming that we don't have any air resistance or anything like that, and so we'll just add very subtly in a vacuum. For our purposes, we will neglect air resistance, so don't even worry about that. Okay, good. And so now we have these two types of energy, but let me just present them more formally for your own notes. We have our kinetic energy, which, just in as few words as possible, I will describe as the energy of motion. And the energy of motion is dependent on mass, the mass of an object. So a more massive object that's moving has more energy than a lighter object that's moving. I tend to agree with that. But the velocity is the more important term. It's squared. And that square has a huge influence on what the energy value actually is. So if I have a velocity of 5, let's say, right? That's going to give me a kinetic energy. But if I double that velocity to 10, then my energy isn't doubled. It's doubled squared, so 4 times larger. And so the square is a very big part of this. When we measure kinetic energy, and when we measure any energy, the units look like, at least for kinetic, that they should be kilograms, meters per second squared, like that. That corresponds to mv squared, as we see over there. And so let's think of another name for this. That's a very complicated looking unit, and we call these joules. So we're going to use the capital letter J as our unit for energy instead of the kilograms meter squared per second squared. All right, so now on to gravitational potential energy. This is a little more complicated to write a simple definition for, but let's say this is energy that's associated with the position of an object. I like that, with the position of an object in Earth's gravitational field. And so that's a simple enough explanation for now. We'll get used to how to use it. But all it's saying is, look, if I have an object, it has some mass, it's in Earth's gravitational field. I'm still here on Earth, despite looking like I'm inside the notes, I'm still on Earth. And as I move it here, it has a different gravitational potential energy than if I move it down here or up here. All of these positions have different gravitational potential energies, and we can quantify that value through the use of mgy, mass times gravity times the y position. Now, some people who may have seen gravitational potential energy in high school will have seen an equation mgh, mass times gravity times height, and that is wrong. Wrong is the wrong word. It is very limiting. Using mgh and always using h to describe the height from the ground is going to limit your ability to do difficult problems. So don't use mgh, use mgy. And you're saying to yourself, well, what is y? Isn't y just height? No, y is whatever you want it to be, because you're going to always set your initial height. And you will find that in more complicated problems, it is not efficient to, it's not the best way to do a problem. And in some cases, you can't really do it if you're always making the ground your y equals 0. So you're going to be measuring your height from a different position depending on the nature of the question itself. And that's why you use y and not h at all. The SI units, of course, are the same because it is energy. All types of energy have the same unit, and that is joules once again. And now, for the best part about energy, the thing that's going to make energy much, should I say it? Should I say it? Sure. Easier than forces. Energy is easier than forces. And the reason it's easier than forces is because energy is a scalar. It's not a vector, meaning I don't care about the components of energy. Energy has no direction. There's no cos and sine and Pythagorean and angle. None of that occurs in energy because energy is a scalar. It is a quantity that describes the ability of an object to do work, have work done on it, and it is not associated with a direction. And that's going to make our problem solving much, much easier. And so what we're going to do now is a small example, very, very straightforward, but we're going to do it in a way to prove to you that basically that the gravitational potential energy is a relative quantity. It's not an absolute value. Like when we talk about the gravitational potential energy of something, we're always talking about it relative to a position. It has no true value in this context. And so we're going to do this problem. Let's take ourselves a 275 gram ball, and we'll do a free fall problem where it's released from rest at a height of 1.5 meters above the floor. So let's say even the floor of your room, it doesn't matter, 1.5 meters is about here, right? So we'll let go of our ball at that height. Now we're going to say that this height is also, let's say you live quite a bit away above sea level, say 106 meters. 106 meters above sea level. So these are all the same position. I'm describing in different ways. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Your question is, what is the ball's speed just before it hits the ground? And you're going to use, in this case, energy. So you might be able to solve this problem using kinematics, but that's not what I'm asking for. I'm asking for this solved with kinematics. So before you get started, don't get started just yet, because I'm going to assign a different value of your initial height depending on, let's do it by your first name. Because I want everyone to do this problem in a different way and then realize that we're all going to get the same answer. What do I mean by that? Well, there's no right place for us to measure our position at y equals 0. There's no right place to give ourselves a height relative to another object. Should we say that y equals 0 at the ground? Should we say y equals 0 where we started from? Should we say y equals 0 at sea level, that we're doing everything relative to sea level for some random reason? None of those are better than anything else. And so I want to make sure we understand that. And so what I'll ask people to do is try this problem in one of the following three ways. You could choose which way you do it, or for fun, why don't you do it by the letter of your first name? So if your first name starts with the letter, let's see, what's about a third of the alphabet? 8. Let's say H, A to H. Then I want you to use y equals 0 at the floor of your room. And so we can draw that problem where we have our initial position here. Now remember that it was 1.5 meters above the ground. And eventually it's going to hit the ground, but right before it hits the ground, we want to know what the speed is, and we're going to call that a height, y final, of 0. And we'll make plus y up as we always do. So if your first name begins with A to H, get started on that. For those people whose first name is I to, let's not go too far, although we're going to run out of people. Let's say I to P. Let's make your y equals 0 sea level. And for you, we have y initial is equal to that location, y final equals this location. We still have our plus y up, and so we're saying that your floor, where it ends up, is 106 meters above sea level, and so where it started from is 107.5 meters. And so if your first name begins with I to P, please use that as your initial and final values. And finally, for everyone left over, including myself, so that's Q to Z. Rupinder falls under R, of course. So I really should be doing this one, where y equals 0 at the dropped point. Okay, and so here we have our position here. And I'm saying that y initial is equal to 0. I'm still going to use my plus y is up. And this is a standard move I used to do in my projectile motion problems, even in my free fall problems. It's not weird for me that the final position is negative 1.5 meters. Okay, so go ahead and do the problem in your way, and then let's compare answers. I will do it the third way. Regardless of which of the three you have, you're going to use our conservation of energy equation for free fall. We have shown that the initial kinetic energy plus the initial gravitational potential energy is equal to the final kinetic plus the final gravitational potential energy. And so go ahead, since this is the first time we're using this, we don't know which one's zero, which one, etc. Let's put them all in. Let's put them all in. And we write this as 1/2 mv squared initial plus mgy initial is all equal to 1/2 mv squared final plus mgy final. There we go. And so if any values are zero, now is the time to put them in. And so I haven't put anything about velocity, but we know how free fall works. This is an object that is dropped at 1.5 meters, and we're trying to find out how fast it's going at the ground. That means the initial velocity should, of course, be zero. Absolutely. In all cases, we have v initial equals zero for our dropped problem. And that means I've got v initial 0, so that whole bit goes to 0. I have y initial 0, so that goes to 0. Wow! According to this, my initial energy is 0. That's a little bit surprising, a little bit. Is that okay? Does that mean one of these two has to be a negative energy? Can I have a negative energy? Sure, you totally can. A potential energy can be a negative value. And so rearranging for this, we'll move our, what are we looking for again? Final velocity, right? So let's move this one over here. Mgy final is equal to 1/2 mv final squared. Turns out that the mass of our ball did not matter, and we can solve for v final as simply equal to the root of negative 2gy final. Now, if you did one of the other two methods, your equation will look different, but your final number should be the same. In fact, if you did the middle way, you would have a more complicated equation at this point to do. And I end up with negative 2 times 9.8 times negative 1.5 as my final position. Throwing those numbers in, I get my final velocity, and I hope you did too, regardless of which method you used, of 5.4 meters per second. There we go, there we go. And that gives us our final velocity. You can check that for yourself, maybe even use your kinematic equation to get that. And what we've realized by doing it this way, and everyone else getting the exact same answer, I guarantee, as long as you did it right, is that the method doesn't matter. Basically what it means is it doesn't matter where you make y equals 0. And what that tells me is that gravitational potential energy is not actually a real quantity in the sense that it has a true number in the way that we've defined it. All it means is that the change in gravitational potential energy is what matters in a problem. How we go from this position to this position, that difference in energy is going to be the same regardless of where you set your y equals 0 term to. And so in that case, what we want to do is to use our initial and our final position as we have them, regardless of what we set them to. So you can set your ground to y equals 0, you can set your initial position to y equals 0. I wouldn't recommend setting it to sea level, that's kind of silly, but there will be other places that you want to set y equals 0 to as well, as we'll see for more complicated problems. So all we've shown is that gravitational potential energy is relative, not absolute. So now let's introduce our third energy. This is an energy we mentioned briefly, and that was a spring or elastic potential energy. And so what is that? Do we have an equation for it? Where does it come from? So this is the elastic or spring potential energy. You can use those words interchangeably. I think elastic is a little more general, meaning you're dealing with a few more things, but conceptually they're the same. And the potential energy associated with an elastic or a spring is that which wants to restore an object to its original shape. And so when we saw that example of the pole vaulter, they had that long straight pole, and when they were running and they used their gravitational potential energy to bend the pole, and that bent pole stores a lot of energy. It stores a potential energy, and it wants to go back to its regular shape. Objects that are bent out of their regular shape, many of them have the ability to return to that original shape. And so what you're basically doing is you're putting energy into the object such that it's storing it until it can return back to its regular shape. And then it's basically using that stored energy to return itself to its original equilibrium position. And so the most obvious example of this is a spring, but you could use a ball, same sort of thing, right? A ball has this shape, and if I was to squish it down like this, it wants to go back to its regular shape. So it's actually quite hard to squeeze it because it prefers to be at this shape. And so that spring bouncing elastic energy is going to restore it to its regular shape. Now, to understand this type of energy better, let's actually start with a force. It's a force we did not talk about originally in our list of forces, but we're going to introduce it now. We won't use it when we're doing energy questions, but it will help us to understand where the equation for elastic potential energy comes from. It comes from the idea of a restoring force. So we get a restoring force in systems. So this occurs in systems that exhibit a natural or internal force to return to its original size, shape, and position. And so not all objects do that. When you move some objects around, they can break, they can happily be moved into another space without bouncing back. You can think of like Play-Doh, for example, doesn't have too much restoring force. But things that do have a lot of good restoring force are things like springs. And so if I take a spring and I stretch it, it wants to go back to its original size. If I take a spring and I squish it, it wants to bounce back to its original size. Same with elastic bands. And balls as well. And so now I have a couple of examples of things with restoring forces. Here's your typical elastic band. Again, sort of thing. I can pull it back like this. Take the band, I pull it back like this, and now it has a lot of stored potential energy, such that if I let it go, should I? No. Oh my gosh, it's fine. So the energy is released and very quickly transformed into kinetic energy. We can see the same sort of thing with this spring right here. This is actually a slinky, not a traditional spring. And so it doesn't have too much restoring force, but if we lay it out kind of in a horizontal way right here, better horizontal, apparently it's tipping back to me a little bit, you can see it's in its nice natural equilibrium position. And if I should squish it, now there's energy stored within the slinky itself, such that if I let it go, it goes back to its original position. So it's not a strong spring. And I can do the same thing by stretching my slinky. Let it go. Again, it returns back to its original size and shape. And so this restoring force is naturally in these sorts of objects, and it not only is a force, but we can transform that into an energy. The thing for us to do would be to quantify this force. And the value of our restoring force is given to us through something called Hooke's law. Hooke's law is just the equation for the force, specifically on a spring. And it's springs that we're mostly going to use in this basically in first year physics. Springs are the classic example we use to understand the restoring force. And Hooke's law specifically gives us a force equation. Now this is like any other force equation. We had the frictional force equation with gravity equals, force of gravity equals mass times gravity. This one is specifically minus k times delta s. Minus k times delta s. Where our k is going to be a new quantity. This is lowercase k. And it is called the spring constant. And basically the spring constant holds all sorts of properties of the spring itself. And those properties include size, shape, number of loops, what it's made out of, etc. And what that does is it gives us the strength of the force that it wants to return to. So for example, the K on that slinky is probably very, very small, such that we ended up not having much of a restoring force. But if you had a very strong spring, you would have a stronger, higher K. The SI units for the spring itself is given in units of newtons per meter. And you can see that because delta S, we're going to find out, is displacement. So if you're solving for that, it's just force divided by displacement value, which is given in meters. And so our units are newtons per meter. That is our spring constant. Our delta S term in this question is going to be our displacement from equilibrium. Unlike with our gravitational potential energy, where we had the ability to choose where our 0 point is for energy, you don't have that choice with a spring. A spring has zero force on it when it's in equilibrium. And so if I displace it from equilibrium, either by squishing it or stretching it, then I am increasing the force on that spring, as well as, we'll see, increasing the energy as well. And so let's just make sure we understand delta S graphically. And so I'll create a few diagrams of horizontal springs. Horizontal springs are a little bit easier to understand than vertical springs because you don't have to take into account any gravity situation. And so what we'll do is draw 3 springs. Our first one is in equilibrium. And so this point here, let's call it S sub E. And that's our equilibrium position, which we will set to 0. Our next one will be our first stretch spring. So it's the same spring, but we stretched it to about there. That looks a little bit too big. Let me make it a bit smaller. Let's say about there. And so now we're at this location we call S. Our equilibrium position still remains the same, and our delta S is therefore equal to whatever position we are minus where we initially were. The same exact thing happens if you squish your spring. And we end up with a spring here, this location S, again compared to our original equilibrium position, is governed with that equation. Okay, so now that we've talked about the force required to squish or stretch a spring, let's see how that's related to the stored potential energy in that string. So, the stored potential energy in a spring or elastic object can be converted or transformed into another form. And that could be gravitational potential energy. Oftentimes it is kinetic energy, but we'll see for different questions. It might even be both. For our pole vaulter, it was gravitational potential energy, but we can think of circumstances where it would be kinetic energy. And so all we need left to do is to give ourselves an equation for the gravitational potential energy, and it is equal to 1/2 K times delta S squared. Interesting. Okay, take a look at that equation. Really absorb it. We got K, our spring constant. We got delta S squared. And so this time, it kind of reminds me of 1/2 mv squared, but it's 1/2 K S squared, where K is the properties of the spring itself. And so it's kind of like, masses for an object. The K is, it's not the mass, but it tells me about the object. And delta S is a position. How far away from equilibrium are you? Well, you got to square that value to get the energy stored. So again, you double the distance from equilibrium, you're going to quadruple the energy stored, which is of course measured once again in joules. Okay. So what are we going to do with this third energy? Well, we are adding this type of energy to our list of conserved energies. Now, we haven't proven or shown that all energy is always conserved. Can it be converted to a type that is not useful? Does it leave the system? All these questions remain unanswered. But we do have 3 different types of energy: gravitational potential energy, kinetic energy, and now spring potential energy that we have stated are conserved quantities as long as we're using what's known as a massless spring. Basically, it means it doesn't weigh too much and we don't need to take its mass into account when we're doing our problems. And so now what we'd like to do is to do some examples that include the spring potential energy for our list of energies, and see what problems we can do with 2 or even 3 of those energies put together. That's for another video.